So this question can be difficult if we do not recognize that this is a top view. So we could picture this setup being on a table, and this is like the spinner in a game or something like that. That's really important. Here's our hinge location. We're told that there's this thin rod, and it's a frictionless surface. It's struck by a sphere with a linear momentum of pi. The sphere rebounds. All right, and this is where we should be thinking about rebounds. Okay, so if this had a momentum of pi, the change in momentum is going to be p0 minus p final, which we know is equal to twice the magnitude of pi. That's going to be the change in momentum of the ball. Law of conservation of momentum says the total momentum of the system must remain constant. So if the sphere has a momentum in this direction equal to a magnitude equal in this direction, then the rod must have momentum in the other direction. So the angular momentum of the rod is mvr. mvr. The mv that we're getting, the momentum part, is twice that. 2mvr. In this case, r is d. So we have 2mvd, which is choice D. Now, you might be saying that the delta P is P0 minus PF. All right, so we've got PI minus PF. But if we're dealing with the magnitudes, only, this would be 0. We should always be treating this like a vector. And so this is MV and this is MV, but this V is negative. We have to choose an answer here that shows we understand that the change in momentum is equal to twice the magnitude of this. Twice the magnitude of the initial momentum. And they want the magnitude. If we choose this, this implies 0, or it's ambiguous. This here really is we're saying, dude, it's twice what it was in the beginning. I don't like it because they're not using a vector convention, but just be aware of it. You got to eliminate that ambiguity and show that that's what you mean.